Good evening, everybody. Welcome to Tibbetts Physics. What is crappin' in? Today we're going to talk about conservation of energy, which kind of puts together everything we've learned in this unit so far. So let's just first define conservation of energy. Last unit we looked at momentum and talked about conservation momentum, and we said how the momentum of the entire system remains unchanged. It's only transferred from one form to the other. And that's the exact same thing for energy. So the total energy, let's make this full screen. The total energy of a system, that's the key word, remains unchanged. I should say remains the same. It does change, but can be transferred from one form to another. So if we think about it, all the energy in the entire universe has been there since the beginning of existence. Although it's changed into different forms. In physics, we'll talk about potential and kinetic energy, but there's also thermal energy, mass, which we'll get to later. So it changes back and forth, but the important thing to know is that all the energy before is equal to all the energy after. So we could say the sum of the energy before is equal to the sum of the energy after. If we break down the energies in physics, we have potential, both gravitational and elastic, plus kinetic, and we also have internal energy. And we also have the work kinetic energy theorem, so work can be done to the system. And that's equal to potential plus kinetic plus Q plus W. And all these are before is equal to all the energies after. So if we look at someone that has a bow and arrow, really quick, I guess we'll look at Legolas. There's my bow and arrow. And Legolas is pulling back on the string. So he's doing work on the string as he pulls it back. And since the string is kind of springy, he's given it potential energy. So the work is coming from, or the energy, sorry, is coming from Legolas, who pulls back the string, given it potential energy. And when he releases it, it's then converted into kinetic energy because it's moving. So if we look at the energy of the entire system before and after, it's going to be unchanged. It just goes from one form to another. Let's look at the roller coaster. We kind of talked about that last video and labeled it. So let's just label it really quick. This is a classic physics example. So let's say we have a roller coaster at point A, B, and C. And at point A is the max height, and B is at ground level. So at maximum height, what type of energy does a person or the roller coaster have? Well, it's at the maximum height, so it has potential energy. At the bottom, at B, it's at ground level, and it's moving at its fastest speed, so it has only kinetic. In this case, we can say the potential energy at A is equal to the kinetic at B, because the energy goes from potential to kinetic. And then at C, this time it's like midway through the heights, so it has both kinetic, because it's moving up the hill, plus potential, because it's at a height. So again, the energy of the entire thing remains unchanged, but it's transferred from one form to the other throughout the entire process. We're going to go through quite a few demos when we get back from vacation. Now to help us analyze those, we're going to do what we did for conservation of momentum, and we're going to make LOL diagrams. I think we enjoyed making those. That's hopefully not sarcasm. Okay, so just like before, we have all the energies before. By before, I meant momentum. And the possibilities are potential. We could break that down into spring or elastic potential energy and gravitational, kinetic, internal, and work. If you're doing work to speed something up, it'd be before. If you're doing work to slow something down, it'd be after. So after, we also have potential, kinetic, internal, and work. And we can put an equal sign here, but usually what we like to do is there internal energy? I guess we'll make that a Q. Is there internal energy? So like before, we look at the scenario given in the problem, and we'll analyze it based off of our LOL diagrams to help us build the formula. We know the total before has to equal the total after. We have to know what part of each energy we're looking at. Now, speaking of vacation, I don't know about you guys, but I'm not one for family gatherings. You're sitting at the Christmas table, and the conversation is so boring and so dull, and I start fantasizing, what if I just jumped out that window back there? I jump out of it, there's glass all over the place. Everybody's like, oh, what did Kyle do? So I come back inside, and I start scraping off all the glass shards off of me. And they say, Kyle, what was wrong? I'm like, nothing, I was just bored. And I look over at my aunt and I say, hey Aunt, by the way, how's your stamp collection going? I think I missed that conversation. So, let's analyze me jumping out the window at my family's house. So let's say this is our example, a 60 kilogram Kyle, lowercase, jumps out of a 10-meter high window. For some reason, their kitchen is on the second floor. And we want to know, how fast was I going right before hitting the ground? Right before hitting the ground. Alright, so let's draw an LOL diagram. Before, after. And we'll label our befores and afters. So before, potential, kinetic, work, internal. So before, I'm standing at the 10-meter high window, and because it's a height, I've got gravitational potential energy. And before I jump, I'm not moving. There's no work being done on the system, and there's no air resistance when I'm standing at the top of the window. After, same thing, potential, kinetic, work, internal. I'm at the ground, so I don't have potential. I'm moving at the bottom, so I have kinetic. No work was being done. And in this case, we're neglecting air resistance. So all we do is write out our formulas based off our LOL diagram. So we've got PE before is equal to KE after. And we want to figure out how fast I was going. So what we do next is we just expand our formulas. Potential energy before is mgh before. Kinetic energy is 1/2 mv squared after. And we're solving for VA. So we'll multiply both sides by 2, divide by m, so the m's cancel out, so my math doesn't even matter. And we'll take the square root. So we've got V after is the square root of 2GH. Plug and chug. V after is the square root of 2 times 9.81 meters per second squared times a height of 10 meters That gives me a velocity falling out the window of 14 meters per second. And that's a quick look at conservation of energy. Again, we'll do some more demos in class. The next video is going to go into some more LOL diagrams that involve both work and internal energy. That's it for me today. See ya.